You need to have I posted on ClassJump the these problems that I'm gonna solve on this video. And if you go into ClassJump, it would be on after the practice exam. You print it out or you have it open, and at the same time you can be solving the problem with me. So 400, let's start with the first one. At 439 grams of sample of water absorbs infrared radiation at 1.0 by 10 to the fourth nanometer. What is that? It doesn't say if it's wavelength, frequency. What is it? It's a nanometer. So how I said the units help us recognize what the problem is giving us, what data is it giving. So the first thing, as usual, I write down what are they giving me, and from a carbon dioxide laser, suppose all the absorbed radiation is converted to heat. Okay, so let's put that all radiation is equal to the heat, just in case, to see what do we need it for. Calculate the number of photons. Okay, at this wavelength. Which wavelength? The one they gave us. To raise the temperature of water 1 degree. What is a raise of temperature or a decrease? It's a delta T, right? 4.00 degrees Celsius. Now they're asking for the number of photons. And if you think about it, they're giving us the grams, right? I'm sorry, the mass of the water, and this is water, of 439 grams. A mass of 400. So if they're giving you mass, they're giving you a change in temperature, an increase in temperature of 4.00 degrees Celsius. If they're telling you that all the radiation is converted into heat, sorry, all the radiation is converted into heat, means that the energy of the radiation would be equal to the energy, to the heat, or the energy produced, or the energy absorbed, which will increase the temperature in 4 degrees Celsius. Meaning that the energy of the radiation is going to heat the water, right? And increase heat water and increase the temperature of the water. So what if here we got the formula of Q equal mass by specific heat of water by delta T? Remember that from last chapter, from chapter 5, in which, because think about it, they're giving us mass, they're giving us delta T. Why don't we use this? And they're saying heat. Now you know that this is the same as the energy of the radiation. Now, this is a total energy, right? What would be the energy per photon? Mm, so what if we find this total energy, right? And we find the energy per photon, where do we get it from? And I don't know if you remember this formula, you will have it anyway. It's the constant multiplied by frequency. And you know anyway that c, speed of light, is equal to wavelength multiplied by frequency. So the frequency would be equal to c over wavelength. So now, if you have this as heat, if you have this as the energy of photon, what if we divide the total energy, we divide it by the energy per photon, and we can find out the number of photons. Okay? And that is, if we have a total energy, right? How many photons? It's like you got the joules per mole. How many photons will produce that energy per mole? It's kind of the same. The total energy, remember, photons is like um, the quantum is the minimum amount of energy, the photons, and it's like little package of energy, and they're 10 to the 23rd in each atom. So this would be the number of photons. And energy, the energy, this formula, the Planck constant, multiplied by the frequency is the energy of a photon, of one photon. Always remember that. So if you got the number you got here, the energy of a photon, you can find out, and you get the total energy, you can find out the number of photons. So if this here, let me put it in, is this equation number one? Is this one? And number two energy will be this. Let's find out the values for each one, okay? And then find out the number of photons. Why? Because this is a total energy, the one that changed the water from 4 degrees Celsius. So we got here, let's keep on then calculating it. Let's start by calculating the energy of a photon. What is the wavelength we're going to use? They're telling us every time they give us a wavelength and frequency, we're going to calculate the energy of a photon. So let's start also. Let me do it here. Okay. So I'm going to erase this, right? And I'm going to write here that the wavelength. Why is it that I'm going to use that? Because when we're going to plug in this formula, by the way, let's go ahead and get the frequency here. You can do it in two. Find out the frequency first and then calculate the energy. But I'm usually doing, to save time, that frequency would be equal to C over wavelength. Okay? But as you see, C is equal to 3 by 10 to the 8. All those constants, you're going to have it in the exam. Meter per second. And H equals 6.626 by 10 to the minus 34 joules multiplied by second. So if this constant is in meter per second, we always have to convert. If we're using the lambda in the formula, we're always going to have to convert to meter, centimeter to meter, nanometer to meter. So in this case would be 1.09 by 10 to the fourth multiply by okay, nanometer multiply by 1 meter. It's equal to 10 to the 9 nanometer. So nanometer and nanometer cancel out. So it would be 1.09 by 10 to the minus 9. 1.09 by 10 to the 4 minus 9 would be minus 5. And this would be meters. So let's take this value of lambda and get it in this formula to calculate the energy per photon. So the energy per photon would be equal to H, which is 6. It's already there. 6 to 6 by 10 to the minus 34 joules per second multiplied by the constant. You're going to have all the constants. Meter per second divided by the lambda we found here, which is 1.09 by 10 to the minus 5th. So minus 5th. And this would be meter. So meter and meter cancel out, second and second. So the energy of a photon would be equal to, I'm going to do the digit part how I do and then the exponential to avoid problems with the calculator. So now I add and subtract the exponential. And this would be a plus 8 plus 5 because this is on the bottom. So it's going to be energy of a photon is equal to, this is going to be 13 mhm, minus 31 is minus 21. So this is going to be 18. I got the numbers already. That's why it took me a lot to start because so I don't have to start calculating all this. Just double check, but I calculate all this. I know I got the answers right. Minus 21 joules, of course, per photon. I'm not gonna move this yet. Okay, this until I finish the calculations. It doesn't matter if it's not, but in scientific notation would be if I move the decimal to the left, it would be 1.8, 1.8 by 10 to the minus 20. But I'm not gonna move it because I did it like that before the calculations. So I don't want to be in the middle of this messing it up. So we got here, this is the energy. Now, how can we find, we got this one, the first one. How can we find the one, the energy, the total energy of the sample? Well, we know the temperature, we know the mass, and it's water. So that's another constant you're always going to have, and it's the specific heat of water. So using this formula one, right? We're going to go ahead and plug in the values we have. And just as a reminder, specific heat of water would be 4.184 joules per grams per degree Celsius. So using this, we have the mass, which was, if you get the piece of paper, 439 grams multiplied by 4.184 joules per grams per Celsius. Multiply, remember, it's an increase, it's saying it's not one temperature or another one. We don't need it. It's a delta T already. So we plug in here 4.00 degree Celsius. And this Q, which is going to be the total energy, is equal to, and this is the value I got, 7,347.104. And this would be joules. Now we got it. So having this, right, we know by that the number of photons, how I said, if we divide the total by this, the energy per photon, we can find out the number of photons. So the number of photons would be equal to the total energy that it that it was that it was the energy used to heat the water 4 degrees Celsius. 347. Let me leave the decimals and all the sig figs now. Joules, right? And by the way, it's 3 sig figs what we're gonna need. Divided by, at the end, 18.237 by 10 to the minus 21 joules per photon. And that's gonna give us the photons on top. Is equal to, that gives me 4. And again, I did the digit part. I divide this by this and then move the exponential to the top. It was going to be 400.86 by 10 to the 21st, 21 photons. And if we move the decimal 2 spaces to the left, it would be 4.03 3 sig figs by 10. We add 2 here, up photons. And that's the right answer. You can do it with your calculator, but this is the right answer. What I did here is divide the digit part, which is all this, right? And it gave me 402.86. And then the exponential, I move it to the top with a positive sign. And then I move the decimal 2 to the left. So I would have it in standard scientific notation. And then moving 2 means that I have to increase the exponential by 2. So that's the right answer for this. Let me do problem number 2. A microwave oven. This is very similar to the other one, but it has a little things, additional things we have to do. A microwave oven operating 1.2 by 10 to the 8. Again, this is lambda. 1.22 by 10 to the 8. And lucky that we have the nanometers. Is used to heat 135 milliliters of water. Now this is the volume, is 135 milliliter of water. Very similar to the other one, but in this case it's milliliter. But if the density of water, we take it as 1.00 grams over milliliter, we can already assume that it's 135 grams. Why do I'm taking it? Because again, we're going to use the heat. See, we got a change in temperature. In this case, we got a final temperature of the water of 100 degree Celsius, an initial temperature of the water of 35.0 degrees Celsius. And it says calculate, very similar, the number of photons. But there's a little bit of difference. That's why I wanted to do this one. And it's a photon needed it if 92.3% of the microwave energy And now all the energy, all the wavelength is not going to be converted. The radiation is not going to be converted to thermal energy like we had on the prior problem. We had that all of them was 100%. So in this case, I said that the total radiation, it was equal to the total heat. In this case, it's not the same because it's only 92% of the microwave energy is converted to thermal energy of heat. So it's 92.3% of the microwave energy. So I would put it that is the light energy, so I would put the energy of the photon only at 92.3%. So we use the same equation to calculate the number of photons. The only difference is that we have, first of all, we have to calculate the Q using the two temperatures. And here we have to be careful because the energy of the microwave, the energy of the radiation emitted by the microwave is only going to produce it at 90%, at 92.3% is going to produce the heat. So what we have to do is to calculate that, we have to again divide the total energy by the energy of the photon. And this is the energy from the microwave. So what do we have to do first? Let's calculate the energy of a photon. And then we multiply by 0.923 because we only are going to use a 92.3%. Let's start with that. Let's calculate again and let's use our prior formula on the prior problem, and it was the photon, and we know already. Let me plug it in because we did it already by 10 to the, this is the Planck constant, joule multiplied per second, and then the frequency. Remember the frequency, it's equal to C over lambda. So C would be 3 by 10 to the 8 meter per second. And our wavelength here is easy, 1.22 times 10 to the 8. Ah, but sorry, but here we have to convert it to meter. So we multiply by 10 to the minus 9, and this would be meter over nanometer. So in this case, we should have 1.22 by 10 to the minus 1 meter. Sorry for that. Oh, let's do it here. This would be, instead I nanometer by multiply by 10 to the minus 9 meters over nanometer. So now we know nanometer, meter, second, and second. So I do this, cancel out. So this would be on top with a positive sign. So the energy of a photon, I do the digit part, 6.626 by 3. You do it how you wanted to do it, but please do not make an exponential mistake. By then we got 10 to the minus 34, and then we got this minus 9 goes on top plus 9, and this would all be used. So this would be energy of a photon. I solved the digit part, this by 3 divided by 1 point, And this is minus 34 here. This and this cancel out. And we got left minus 9, which is going to be a positive on top. And this is going to be mhm, this is going to be 16.29 by 10 to the minus 24 joules. Now this, right, you have to multiply by 92.3 divided by 100. Why? Because it's only a 92.3% of this radiation that is converted into heat. So this is going to be the energy of a photon that is converted into heat is going to be equal to, if we do all this operation, or by 0.923 is the same thing. So because it's at 92.3% of this. So this would be 1.50, right? By 10 to the minus 24 joules. Just review my calculation but they are perfect. So now let's go ahead and find out. Now we have to go ahead to find out the number of photons. We still need to finish the this little equation, remember, but we still need to find out this, right? And this we were going to find it out. We found it out on the prior problem with the Q. So if you got Q equal the mass, which is 100 by specific heat of water by delta T. And that's our little formula. So let's go ahead and find out, right, the Q. So Q would be equal to the mass. If you remember and you wrote it down, it's 135 grams. So it's 135 grams. Now this constant is always going to be given 184 joules grams. So sometimes I don't give it to you on the problems because at home you have the internet tables book. Okay, so the final temperature would be 100.0 and the initial 35. That's the change in the temperature of the water. Minus 35.0, and this all is degrees Celsius. So degrees, grams, and grams. So this Q, okay, and I did it already, the calculation, is gonna give me 36,714, and I'm gonna leave it in joules because joules. Now to find out the number of photons, remember we have to number of photons would be equal to the Q, which is the 36.714.6 joules divided by the energy of the photon, which is already, and it's a 92, 150 by 10 to the minus 24, divided by 1.50 by 10 to the minus 24. And this would be joules per photon. And joules cancels out, so it's giving me the number of photons. So this is gonna give me, again, 24. How I do it, I take the 24 up and I divide. And let me do it real quick. I'm sorry, this is 36,714.6 divided by 1.50. This is my digit part, how I said, by 10 exponential. This goes positive on top. So this is gonna be, right, 24. And this is gonna be photons. And this is equal to 24, 24,476 by 10 to the 24 photons. Now, if you move the decimal to scientific notation, right, the decimal's here, you need to move it 1, 2, 3, 4. So that means that the number of photons, you move it 4 spaces, right? 2.45, because I'm rounding it to 3 sig figs, right? By 10, so I need to add 4 to the 24, 28, and that's the right answer. Let me cut it down and post it, and tomorrow I keep on going. We have already 31 minutes, and it's a long time.